Good morning, students. Myself Vaidegi, working as assistant professor in Sri Muthukumaran Institute of Technology. Today the video lecture is from the subject EC 3452 Electromagnetic Fields for the 4th semester ECE student. Today the video lecture is from the unit 5 of EMF. First we see about the introduction. In this lecture, we will discuss plane electromagnetic waves, which is an important topic in electromagnetic fields. Electromagnetic waves are generated due to time-varying electric and magnetic fields. Electromagnetic waves are generated due to time-varying electric and magnetic fields. These waves can travel through free space as well as through material media without requiring any physical medium. The concept of electromagnetic waves was first predicted by James Clerk Maxwell through his famous equations. Examples of electromagnetic waves include radio waves, microwaves, infrared radiation, visible light, X-rays, and gamma rays. Understanding electromagnetic waves is essential for communication systems, radar, wireless network, and many other modern technologies. Next we see about the plane electromagnetic wave. A plane electromagnetic wave is a wave whose wave fronts are infinite parallel planes perpendicular to the direction of propagation. In a plane wave, the electric field and magnetic field are uniform over each wavefront. These fields vary only in the direction of propagation. This assumption generally simplifies the analysis of electromagnetic wave behavior. For a wave propagation in a positive z direction, both electric and magnetic fields are sinusoidally with time and distance. The mathematical expression contains the angular frequency and phase constant which determine the wave characteristics. Next we see about the Maxwell's equations. Maxwell's equations form the foundation of electromagnetic theory. They explain how electric and magnetic fields are generated and how they interact with each other. Gauss law for electric field relates electric flux to charge distribution. Gauss law for magnetism states that magnetic field monopoles do not exist. Faraday's law explains how a changing magnetic field produces an electric field. Ampere-Maxwell law explains how electric currents and changing electric fields produce magnetic fields. Together, these equations predict the existence of electromagnetic waves and describe their propagation through space. Next, we see about the uniform plane wave assumptions. To simplify the analysis of electromagnetic waves, certain assumptions are made. The wave is assumed to propagate in only one direction. The electric and magnetic fields are assumed to be uniform over any plane perpendicular to the direction of propagation. The fields depend only on the propagation coordinate and time. The electric field, magnetic field, and direction of propagation are mutually perpendicular. These assumptions help derive the wave equation and analysis wave behavior in different media. Next we see about the wave equation in a medium. Using Maxwell's equations, we can derive the electromagnetic wave equation by taking the curl of Faraday's law and substituting Ampere-Maxwell's law. We obtain a second order differential equation. This equation describes how electric and magnetic fields propagate through a medium. The wave equation shows that electromagnetic waves travel with a velocity determined by the medium's permeability and permittivity. This mathematical model is fundamental for understanding wave propagation in different materials. The equations are del square E is equal to nu epsilon dou square E by dou t square. Similarly, dou square H is equal to nu epsilon dou square H by dou t square. For the general solution is E of z is equal to E naught e power minus j beta z. For magnetic field, H of z is equal to H naught plus e power minus j beta z. Next we see about the Plane waves in lossless media. A lossless medium is a medium in which conductivity is zero. Examples include vacuum, air, and ideal dielectric materials. Since there is no conductivity, there is no dissipation in the medium. Therefore, the amplitude of the electromagnetic wave remains constant as it propagates. All the transmitted energy reaches the destination without any attenuation. Lossless media are often used as ideal models for understanding basic electromagnetic wave behavior. Next, we see about the propagation constant in lossless media. The general propagation constant is gamma is equal to alpha plus j beta. For lossless medium, alpha value is 0 and hence the gamma is equal to j beta. And the phase constant is equal to beta is equal to omega root of nu epsilon. The propagation constant describes how electromagnetic waves travel through medium. It consists of a attenuation constant and a phase constant. In a lossless medium, the attenuation constant is 0 because there is no energy loss. Therefore, the propagation constant becomes purely imaginary and only contributes to phase variation. This means the wave experiences phase changes as it propagates but does not lose amplitude. Next, we see about the electric and magnetic fields in lossless medium. In a lossless media, the electric field and magnetic fields vary sinusoidally with distance and time. Both fields remain in phase with each other. The ratio of electric field strength to magnetic field strength remains constant and is determined by the intrinsic impedance of the medium. Since there is no attenuation, the wave maintains its original amplitude throughout propagation. This behavior is typical of free space electromagnetic wave transmission. Next, we see about the intrinsic impedance of lossless medium. Intrinsic impedance is defined as the ratio of electric field intensity to magnetic field intensity. It represents the opposition offered by a medium to electromagnetic wave propagation. In free space, the intrinsic impedance is approximately 377 ohms. Intrinsic impedance depends on the permeability and permittivity of the medium. The parameter is important in antenna design, transmission lines, and waveguide analysis. Next, we see about the wave propagation in good conductors. A good conductor is a material whose conductivity is much greater than the product of angular frequency and permittivity. Examples include copper, aluminum, silver, and gold. In good conductors, electromagnetic waves experience significant attenuation and as they propagate, most of the wave energy is converted into heat due to conduction currents. Next, we see about the applications. Plain electromagnetic waves have numerous practical applications. They are used in wireless communication system for transmission information over long distances. Waveguides carry microwave signals in communication and radar system. Optical fibers use electromagnetic wave propagation to transmit data over long distance and transmit data at high speeds. Radar system use electromagnetic waves for object detection and navigation. These applications demonstrate the importance of understanding electromagnetic wave behavior. Thank you. Hope you all understood the concept. Next we will see in the next video. Thank you.